Hi, everyone. In lesson 12, we're going to ask, when do we add or subtract probabilities? We're going to look at OR problems in probability. Now, these rules are easiest when we're dealing with mutually exclusive events, or Mees. Mees is my acronym. It's not official. So what's an example of this? Let's say that we're going to roll one die, and we want to look for the probability of getting an even number or a 5 on a standard six-sided die. Let's say that the event even is event A. Let's say that the event 5 is event B, meaning that event A says that the die will come up an even number, event B says the die will come up a 5. Well, there are a couple of ways that we can do this. We could have done this brute force, like we have before. So in the numerator, we count up the number of ELOs, equally likely outcomes, for which A or B occurs, and divide that by n, the total number of ELOs, which is 6 here. Well, let's go through one by one. Let's go through one by one, and let's see what happens. Okay, so one by one, we're going to go through these 6 equally likely die faces and ask, is event A being satisfied or event B being satisfied? A occurs, remember, if we get an even number. B occurs if we're getting a 5. Okay, so we're going to label the appropriate die faces according to their bars. So one by one. If we roll a 1, is event A satisfied? Is event B satisfied? Or is neither satisfied? They're mutually exclusive. That means that they cannot both be satisfied. You realize that we cannot roll an even number and a 5 at the same time. Well, if we roll a 1, well, 1's not even, 1's not a 5, so neither applies. I'll put a big green X here. Neither applies. Oops. What about if we roll a 2? 2 is an even number, so event A will apply. So we'll label that with an A. But 2 is not a 5, B is not satisfied. What if the die comes up a 3? Well, 3 is neither even nor a 5, so we're going to cross out the 3. Neither event occurs. What about a 4? Well, a 4 is even, but it's not a 5. So only event A occurs. Now, what about a 5? 5 is not even, but 5 is a 5. So event B occurs. What about a 6? Well, a 6 is even, but it's not a 5, so only event A occurs if we roll a 6. Okay, so in how many of these 6 boxes, for how many of these 6 ELOs do we have a label? When do we have A or B occurring? Well, if we get a 2, if we get a 2, then that means that event A occurs. Whoops. If we get a 4, event A occurs. If we get a 5, event B occurs. If we get a 6, event A occurs. All right, so for 4 of these 6 ELOs, A or B occurs. So we come up with the fraction 4 over 6, or 2/3. Remember, you don't have to reduce fractions. But there's another way we could have done this. We could have done these event by event. Sometimes that's more convenient. So in particular, this is just a rehashing of this. We could have started by counting up the ELOs for which A occurred. What's the probability that we get an even number? It's going to be 3 over 6, 3/6, or 1/2. What's the probability that we get a 5? What's the probability that B occurs? Well, 1 over 6. And we can just add up these probabilities individually. And why can we do that? Because events A and B are disjoint, or mutually exclusive events, which I'll call Mees. Disjoint and mutually exclusive mean the same things. All right, and that means that they cannot both occur on the same trial. Again, these are mutually exclusive events, Mees, because you cannot roll a die and get an even number and a 5 on the same trial, on the same roll. They cannot both occur on the same trial. In other words, if one event occurs, it excludes the possibility that the other event also occurs on that trial. So even and 5 cannot come up on the same roll. And there's a basic addition rule for Mees. If A and B are Mees, mutually exclusive events, then the probability of A or B occurring is given by the probability of A occurring plus the probability of B occurring. P of A or B equals P of A plus P of B. So the probability of getting an even number, or a 5, is equal to the probability of getting an even number, which is 3/6. Remember? 3/6. We had 3 A's up here, plus the probability of getting a 5, which was 1/6. Remember? We had 1 B up here. 3/6 plus 1/6 is 4/6, or 2/3. The same answers as we got before. So we could go either brute force and figure out which ELOs corresponded to either A or B, or we could have done the events separately, figure out P of A, figure out P of B, and added those results. There were a couple of easy ways of doing this, and both of them worked. We could do a Venn diagram. This is referred to as a Venn diagram, where we have figures and disks representing sets of outcomes. Here's a Venn diagram. All right, so when does event A occur? Event A occurs if we roll a 2, a 4, or a 6. Event B only occurs if we roll a 5. This is not to scale. I realize that disk A should be bigger than disk B, but you get the point. And then if neither A nor B occurs, that happens if we roll a 1 or a 3. They're out here in this space out here, outside the disks. So the probability of A or B occurring is going to be 3/6 plus 1/6, or 4/6. Again, these areas are not to scale. In principle, the areas should be proportional to the probabilities. That should be the case. That was not the case here. But you get the idea. To get the probability of either happening, you add up the probabilities for A and B. P of A plus P of B. All right. So the natural next question is, what happens if the events are not mutually exclusive? What if there are ELOs where both events can occur simultaneously? And that's next time.